often seen as green stripes on an otherwise brown landscape, some of which can be so deceivingly lush that they belie the desert environment which surrounds them. And what's important is that Arizona has lost almost 90% of its historic riparian habitat to both development and agriculture, so that preservation in locations such as the national parks is imperative to keep them going. And finally, these locations are often places of just exceptional natural beauty. Now, before I get too far along, I'd like to just give an outline of what I'm going to be talking about tonight, starting with just a few canyon facts and some little tidbits about springs and seeps themselves. A look at the geology and the hydrogeology, which are the mechanisms for bringing that water to those springs and seeps. Some of the past research that's been done within the park, and then on to current research, including springs classifications, gauges and spring monitoring, and springs inventory and the collection of baseline data. From there, I'd like to move on and talk about some of the threats to these systems, including groundwater use, uranium mining, and climate change. Finally, a quick look at what's next, what's on the horizon for the program, and then tying it all up, hopefully, in a short summary. So Grand Canyon National Park encompasses about 1.2 million acres of north central and northwestern Arizona. Has a visitation of between 4 and 5 million people per year. Has a wide variation of elevations from about 360 meters or 1,200 feet down at Lake Mead to over 2,700 meters, almost 9,000 feet on the Kaibab Plateau at the North Rim. There are over 300 side canyons to the main canyon itself, and an estimated number of springs and seeps exceeding 600. Now, even with that large number of springs and seeps, only 0.01% of the park is actually occupied by these locations, yet 36% of the total riparian flora in the park are found there. Additionally, they have between 100 and 500 times the species diversity than the surrounding arid landscape. So a look at the geology and hydrogeology will give us an idea of where the water for these springs and seeps actually comes from. Now this photo is a good example of some dissolution enhancement of fractures in the red wall limestone, which look like great pathways to move some groundwater. So only a small percent of the precipitation that actually falls on the plateaus surrounding Grand Canyon is actually recharged into aquifers. Rough estimate, probably about 2%. Now it's the rapid infiltration into the Kaibab limestone and some of the other cap rocks around the canyon that are imperative to get this water into the subsurface so we can take it into these aquifer systems. Where otherwise, it could be lost. The potential for losses due to evaporation and transpiration by plants greatly exceeds the actual amount of precipitation that falls on the plateaus. Now this diagram down here on the bottom is a hydrogeologic cross-section of the Coconino Plateau showing Grand Canyon in the south rim right here, the Flagstaff, San Francisco Peaks area here, moving south the Mogollon Rim into Verde Valley, and then the north rim here on the far left. Now on the south side, the geologic units are actually dipping away from the canyon rim. Therefore, the water that is supplying the small springs and seeps along the south rim actually has to move against the regional dip to the north to discharge along the canyon wall. The remainder of the water that's recharged in this area moves southward and then sweeps around to ultimately either discharge in the Havasu Creek system or in the Little Colorado River system. On the north side, the north rim is about 1,000 feet higher generally than the south rim, also receives more precipitation, and also the beds are dipping towards the canyon on this side. So we're getting a larger number of springs and a larger number of higher volume springs on this side. Now the majority of the springs found in Grand Canyon issue from the regional carbonate, what's known as the R aquifer, made up of the Red Wall, the Temple Butte, and the Luau limestones. At the base of this, the Bright Angel Shale acts as a lower confining unit which doesn't allow groundwater transport vertically, so a majority of these springs are occurring at the contact between the Luau limestone and the Bright Angel Shale. Now, looking at a stratigraphic column of the Paleozoic units in Grand Canyon, we can see the rock units that make up these aquifer systems, as well as the units that separate them and act as barriers to groundwater flow. Now, in addition to that R aquifer system that I mentioned, there's another aquifer system that sits a little higher on the stratigraphic column. This is known as the C aquifer, made up of the Kaibab limestone, the Torowik Formation, and the Coconino sandstone. Now, while this aquifer isn't saturated near the Grand Canyon, it is near Flagstaff and is actually an important source of water to the city of Flagstaff and surrounding communities. The water near Grand Canyon is transmitted downward through this aquifer system through a leaky aquitard made up of generally the Hermit Formation and the Supai Formation here, separating the C and the R aquifers. But it's not just the geologic units that either allow or disallow groundwater transport, but geologic structure also plays a major role here. Faults and fractures can act as wonderful conduits to groundwater transport, but it can also act as barriers. Faults and fractures also create a secondary porosity in the rocks and allow for dissolution of limestones and allow these voids to get larger and larger to make them be able to both store and transmit large volumes of water. Now, looking at the R aquifer in the field, we can see the breakout of the Supai and that upper confining unit up here, the units that make up the R aquifer, the Mississippian Redwall limestone, the Devonian Temple Butte, and the Cambrian Muab limestone, and that lower confining unit, the Cambrian Bright Angel Shale. And just as I said, here's Roaring Springs discharging at the base of the R aquifer at its contact with the Bright Angel. So, now that we know a little bit more about how the plumbing of the plateaus work, we can start looking at some of the research that's been done to study these systems. And I'll start with one of the originals, John Wesley Powell. In his famous 1869 canyon expedition, he wrote a lot of springs, and often as a pleasant contrast to the muddy and turbulent and treacherous Colorado River. He often also wrote of these locations in very grandiose and romantic terms, with quotes like, the spray and the sunshine forming the gems which bedecked the wall. I'm not sure if he actually went up to this spring or not, or whether they just floated by, because it's pretty much completely covered in poison ivy. But who knows, maybe it looked a little different 140 years ago. Now, some other important early research, I'm just going to go through a list of these, include LaRue in the early 1920s, who made some of the first measurements of spring discharge. There's some photographs of him from the USGS photo archives up at Nankoweap Creek on the top and then at Deer Creek on the bottom. And you'll see in some photos a little later in the talk that the technology that he's using here to measure this flow really hasn't changed that much in 80 or so years. And we're using a very similar technology today. Metzger in the early 60s produced a great report on the geology surrounding Grand Canyon and how it related to these water resources. Johnson and Sanderson did a report on the spring flow into the Colorado River in the late 60s. And Cooley studied springs in Marble Canyon and in the Little Colorado. Brown and Moran in the late 70s produced a great report of one of the first inventories of spring and seep resources from a number of helicopter and fixed-wing airplane reconnaissance trips. Peter Huntoon, in a long career between the late 1960s and his master's thesis and his PhD dissertation through the 2000s on a number of spring and seep-related topics, including the Kaibab Plateau hydrogeology, karst aquifer behavior, breccia pipes, and other topics. In 1984, Grand Canyon National Park issued a water resources management plan, which talked a lot about the research and the preservation of springs and seeps. And although this was a wonderful document at the time, we haven't had an update since then, and the park is in desperate need of getting a new resource management plan. Montgomery and Associates in the 1990s performed some of the first groundwater modeling on the plateaus surrounding Grand Canyon, looking at how that water is brought into the subsurface and how it's transported and ultimately discharged at springs and seeps along the canyon walls. Monroe and others in 2005 did a wonderful survey of the geochemistry of springs along the South Rim, and Bills in 2007